So when we left off last time, we had talked about all of these units of measurement. We talked about the difference between mass and weight and capacity and volume. And we had just hinted at doing conversions between them. So I want to look at that today. That process of doing those conversions was called dimensional analysis. Dimensional analysis is really the process of using the units to help us decide what operation, what calculation needs to be done to solve a particular problem. In this case, converting units. Later on in our next unit is going to be actually calculating the dosage calculations themselves. Dimensional analysis is a handy tool for converting with our measurements, but it is an essential tool for doing our dosage calculations. So looking at our dimensional analysis, if we had something like 42 gallons, and I want to convert it into liters, I'm purposely choosing a standard to metric conversion. So I'm going between the systems so that this is a measurement that we don't necessarily know offhand exactly what to do. Feet and inches or yards to feet, we already know exactly how to calculate that. We probably don't need to use the dimensional analysis to tell us what to do. So here I'm going to take my 42 gallons. And in order to use dimensional analysis utilizes the rules for calculating with fractions. So to utilize it, I have to turn that into a fraction. So I put 42 gallons over 1. And now I'm going to multiply by a conversion factor. And this conversion factor here, if you recall, is a unity fraction. And in a unity fraction, it's equal to 1. But more importantly, the numerator is equal to the denominator. And we might say, well, that's the definition of being equal to 1. Yes, it is. But the reason I state that separately, the numerator must equal the denominator, is because it's not going to be obvious in the appearance of these unity fractions that they do equal 1 in all cases. So up here, I have an equivalency. Any equivalency can be used to create a unity fraction. The equivalency we're going to use here is the relationship between gallons and liters. 1 gallon is 3.785 liters. Depending on what textbook you look at, in fact, in this textbook, it depends on what page you look at, 1 gallon is either 3.785 liters or 3.79 liters. So back over here to my dimensional analysis, I'm getting rid of gallons, and gallons are currently on top. And the portion of multiplying fractions that we want to utilize here is that cross-canceling. So to get gallons to cross-cancel, I'm going to put them on bottom in my conversion factor here, in the unity fraction. So 1 gallon equals 3.785 liters. Now that we have that conversion factor set up, we are simply multiplying fractions. We see that the units of gallons do cross-cancel out. And now we can go ahead and multiply 42 times 3.785. Gives us 158.97. And that unit on top is liters. On bottom, we have 1 times 1, which is just 1. So that ends up being 158.97 liters. So there we were going from a larger unit to a smaller unit. This is a way to double check. Gallons are bigger than liters. So we're going from a large unit to a smaller unit. If the unit's getting smaller, the number, the amount, has to get larger. Very similar to our scientific notation that we looked at a couple of classes ago. When the power got larger, the value had to get smaller, or if the value got smaller, the power had to get larger. There was that relationship. They had to do opposites. Same here. Whatever the unit does, the number has to do the opposite. Now here, I was very careful to do out that denominator, even though it was equal to 1 and didn't affect anything. The reason for that is we can run into situations where it does affect things. We might have 150 milliliters, and I might ask you how many, paper out of the way, how many fluid ounces does that equal? And so to set this up, I start off with my 150 milliliters. And I make it a fraction by putting it over 1. Now, as we saw in the previous example, any of our equivalencies can be used to create a unity fraction. So we need an equivalency between milliliters and fluid ounces. And the one we find, this is another one that actually depends on what page of the book you look at. You look at one page, it gives you this one. 1 fluid ounce is 30 milliliters. Literally, the very next page says 1 fluid ounce equals 29.9 milliliters. Whichever one you use is fine with me. They're so close, you're not going to make a huge difference in our result anyway. So here, to cross-cancel the milliliters, since they start out on top, I have to put milliliters on bottom. And I am going to fluid ounces, so they'll be on top. So 1 fluid ounce is 30 milliliters. So now again, we go to multiply. We're just multiplying fractions here. The milliliters will cross-cancel out, which is what we wanted. We wanted to get rid of that unit. On top, we have 150 times 1 fluid ounce, which is 150 fluid ounces. On bottom, we just have 1 times 30, which is 30. So this here is different from our previous example. Up here, the denominator was 1, so we were done at that point. It was just 158.97 liters. Here, since our denominator is not equal to 1, we do have to go one step further and divide that out. 150 fluid ounces divided by 30 is 5 fluid ounces. So giving us that result of 5 fluid ounces up there. So as we've seen here, any equivalency can be a unity fraction. And when we're doing measurement conversions, an equivalency is the main source of our unity fractions. But also, any rate can be used to create a unity fraction. If we have a rate that we know is true in a certain situation, that rate can be used to create a unity fraction that is used for conversions. For example, let's say we are driving at a rate of 60 miles per hour, and we are getting a fuel economy of, let's just do 20 miles per gallon. And I want to know what is my fuel consumption in gallons per hour. So to set something like this up, the key is figuring out which of the existing numbers to start with. We want gallons per hour. So what we're going to do is we're going to look for one of the existing units that has one of those values in the correct position already. So if we look at gallons, we want gallons to be in the numerator of our result. We look over here, this has gallons in the denominator. That's not where we want it. And there isn't gallons in the other unit at all. So let's look at the hours. Here we have hours is in the denominator of our result. We look back here, hours is also in the denominator. That tells us that's the unit we're going to use. We're going to start off with that 60 miles per hour. Now that 60 miles per hour is actually going to be written as 60 miles over 1 hour. If you recall from a few classes ago, actually a couple weeks ago now, any rate like that is a unit rate, and we have to write it out. It's actually a comparison between two numbers. Next, I'm going to use this other rate to make a unity fraction. That rate is implying an equivalency. 20 miles per gallon is implying that in this situation, 20 miles is equivalent to 1 gallon of fuel consumption. So we can use that then to create our conversion factor. We want to keep the hours because we want those in our denominator. We do want to get rid of the miles. So I'm going to put miles on bottom in this conversion factor here, my unity fraction. We have 20 miles. Oops, get back here. This is saying 20 miles. We'll put 20 with the miles equals 1 gallon. So put 1 gallon on top. So you can see how that unity fraction came from that rate, and that rate gave us that equivalency that became the unity fraction. So then from there, we have to just do the fraction multiplication. The miles cross cancel out. On top, we have 60 times 1 gallon. That's 60 gallons. On bottom, we have 1 hour times 20. That's 20 hours. And once again, we want to reduce this, like we do with all rates, down to a unit rate. So we're going to divide by the numerical portion of the second number. In other words, just the 20. 60 gallons divided by 20 is 3 gallons. 20 hours divided by 20 is 1 hour. So that is 3 gallons per hour as our unit rate. So as you can see, there are formulas out there that tell us to get your fuel consumption per time. You take your miles per time or distance per time divided by your miles per gallon, whatever. But here, using the units, using that dimensional analysis, we didn't have to memorize the formula. We didn't need to know anything about the formula. It was strictly the units that told us how to line things up and what calculation to do. We've done, the rate here had a couple of different units in it. We've done some conversions with single unit measurements. I do want to look now at some double unit measurements. Let's say that we make the claim. I'll go out on a limb. Let's say I make a claim that I can throw a baseball at a rate of 90 feet per second. Most of you might be sitting there thinking, no way. 90 feet per second sounds incredibly fast, but it's not a unit we're familiar with. We're used to seeing speeds in miles per hour. So let's convert that 90 feet per second into miles per hour. Now remember, the 90 feet per second is really 90 feet over 1 second. So it comes into that actual rate like that, the comparison of the two numbers. In all of our previous example, we only needed to change 1 unit. Here, however, we have to change both units. We have to change 2 of them. So we'll start out, we need to get rid of feet. We want the feet to become miles. So the feet are on top. I'm going to put feet on bottom here. Our relationship between feet and miles is 1 mile is 5,280 feet. So we can see the feet will cross cancel out for us. Now we're in miles per second. Miles per second. The miles are okay, that's what we want, but we need to get rid of the seconds. The seconds are going to have to become hours. So here's where we have to pay attention to our position in our original unit. The seconds are on bottom, so to get them to cancel out, they're going to have to be on top in our conversion factor, in our unity fraction. We don't necessarily have a direct relationship between seconds and hours. I'll go from seconds to minutes. We know 1 minute is 60 seconds. The seconds will cross cancel out here now. We have miles on top, minutes on bottom. Well, miles per minute are close to what we want. We still need to get those minutes to the hours. So Minutes are on bottom here. To get rid of them, I'm going to put minutes on top in my next conversion factor. 60 minutes equals 1 hour. And once again, the minutes will cancel out. And now if we look at our units, we have miles on top, hours on bottom, and that's exactly what we want. So we can go ahead and calculate. So on top, we have 90 times 1 mile times 60 times 60. What is that? 324,000 miles. On bottom, 1 times 5,280 times 1 times 1 hour. It's 5,280 hours. And of course, we turn this back into a unit rate by dividing by the 5280 on both the bottom and top numbers. So that'll turn this into 1 hour. 324,000 milliliter, 324,000 miles divided by 5,280 is, what is that? 61.36, I believe, miles. So that is 61.36 miles per hour is that rate. At my age, that's probably starting to get to be a little bit of a stretch. I could probably still throw that fast, but I'd have to warm up for quite a bit and probably only throw 1 or 2. And my arm would probably hurt for a week. So anyway, the key here was we had 2 sets of units that we used. We were able to convert both of them in the same conversion by simply using a string of those unity fractions, those conversion factors. We can see that in a lot of our medical practices. We can run into things like um, 18 ounces per, let's go gallon. And we want to know, what does that come down to in grams per pint? Oh, just put PT. Well, again, we'll start out, we'll do our 18 ounces over 1 gallon. Turn that into the comparison of 2 numbers for the rate. We have to convert our ounces. We have to get rid of ounces. They're going to become drams. So ounces are on top. We're going to put them on bottom. This is one you may have to look up. Our relationship between ounces and drams is 1 ounce is 16 drams. So now ounces are gone. We're in drams per gallon. We have to get rid of gallons. So I'll put gallons are on bottom. I'll put gallons on top. 1 gallon is, well, 4 quarts would be the next step. So the gallons are gone. We're now in drams per quart, which is 1 step closer. We have to get rid of the quarts and go to pints. We know that 1 quart is 2 pints. So the quarts cancel out, and we again are now in drams per pint, which is exactly the unit we're looking for here. So on top, we'll go ahead and multiply. 18 times 16 drams times 1 times 1. What is that? 288, I believe. Drams. Let me double check that. $18 times 16 is 288. On bottom, we have 1 times 1 times 4 times 2 pints is 8 pints. And we divide that out. 288 divided by 8 will give us 36. As drams pint. If we switch over to using metric units for our unit conversions, for these rate conversions, remember, metric conversions are totally different strategy, totally different method. We don't have to use a conversion factor. We don't have to cancel units. Because in metric conversions, we only have 1 unit for each type of measurement, and everything from there is just a prefix that moves the decimal point. If we recall, we had our main unit, meters, grams, and liters in the middle. Going larger, we had deca, So it might be decameters, decagrams, decaliters. Hectometers, hectograms, hectoliters, and kilo. So kilometers, kilograms, and kiloliters. Going smaller, we had deci. Oops. Should put my A in here. This would be decameter, decagram, and decaliter. Deci would be dg, dm, or dl. Centi, centimeter, centigram, or centiliter, or milli. Millimeter, milligram, milliliter. And going smaller yet, we skip 2 spots. We don't do anything for the 10 thousandths and the 100 thousandths. We jump to the millionths, which is micro. Remember, for micro, we use that mu. And I warned you, in science, chemistry, physics, whatever, we use that symbol mu. But actually, in practice in the medical fields, because of the keyboarding problem, they would use MCM for micrometer, MCG for microgram, and MCL, so that we don't have to go through some sort of process to insert that Greek character into any sort of keyboarding that we're trying to do. And recall that if we're converting here, if we had 4.2 centimeters, and I want to convert that into millimeters, all we did was look at our chart. From centimeters to millimeters, we're moving 1 spot to the right on the chart. Our decimal point moves 1 spot to the right. That's 42 millimeters. Or if I had 290 milliliters, and I want to convert that to liters, going from milliliters to liters is 3 spots to the left on our chart. So my decimal point has to move 3 spots to the left. If there's no decimal point in the number, that means it's at the end. And then we move it 3 spots to the left. So that is 0.29 liters. So if we have rates with these metric units, that's all we have to do is move the decimal points the appropriate amount. If we have, well, let's do 73 grams per liter, and I want to convert that to milligrams per milliliter. Well, we'll go ahead and we'll set up the 73 grams over 1 liter. We're still going to write it out as a full rate as the comparison of the two numbers. But now we don't need to use our conversion factors or any sort of unity fraction. We're just going to go ahead and convert the rates. Grams need to turn from grams to milligrams. On our chart, if I scrolled up to it to get from liters to milligrams, it's 3 spots to the right. So I'm going to take my decimal point, my 73 grams, it's right there. I'm going to move it 3 spots to the right. I have to add zeros. That becomes 73,000 milligrams. Liters have to change to milliliters. I'll put milliliters down here. Well, from liters to milliliters is the same as from grams to milligrams. It's 3 spots to the right. So my decimal point is at the end since there's 1 in the number. So I take that decimal point and I move it 3 spots to the right. That is 1,000 milliliters. And now all it's left to do is to divide this back out. 73,000 milligrams divided by 1,000 is 73 milligrams per 1 milliliter, or 73 milligrams per milliliter. Notice that ended up being the same number. Typically with our metric units, the numbers won't change. The place of the decimal might. Here, both of them went from a main unit to milli, so both moved the same. So the final number stayed the same. We didn't go over units of area, but to talk about pressure, we do need to look at that a little bit. If I'm dealing with my metric units of length, meters, decimeters, centimeters, and millimeters, We typically don't use a whole lot larger than that for areas. When I converted, as we said, from 0.038 meters going into centimeters, we were moving 2 spots to the right, so our decimal point moved 2 spots to the right, giving us 3.8 centimeters. The reason for that was every place on that chart was just multiplying or dividing by 10, so it was just moving the decimal point 1 spot. However, if we look at area units, if I had 0.038 meters squared instead of just meters, and I'm converting to centimeters squared. Now the squared changes the unit, not the numbers. But the thing to remember is a meter squared is 1 meter by 1 meter. If I look at this as centimeters, this is, I'm going to change over. 100 centimeters equals 1 meter. Well, 100 centimeters in this direction also equals 1 meter. That 1 meter squared actually equals 100 times 100, or 10,000 centimeters squared. So even though meters to centimeters is 2 spots on the chart, or multiplying by 100, since this is squared meters and squared centimeters, the conversion factor gets squared. The number itself, like I said, the 3 and the 8, they don't get squared. It's simply the conversion factor. So we're converting by multiplying by 100. 100 squared is 10,000. The net effect, it sounds complicated, but the net effect is actually very simple. What happens is now each spot on this chart is not 1 decimal place, it's 2 because the units are squared. So 2 spots on the chart becomes 4 decimal places. So I move 1, 2, 3, 4. I have to add a 0. That is 380 square centimeters. The reason I bring that up is because pressure is always in a unit of force over some sort of a squared unit. So if we have 3.2 grams per square centimeter of pressure, and I want to convert that into kilograms per square meter of pressure, once again, our 3.2 grams is over 1 centimeter squared. And because these are metric units, we don't have to set up a conversion factor or unity fractions or anything. We're just going to change the units. Grams are going to become kilograms. I looked at my chart. If I had grams, this would be decagrams, hectograms, kilograms. 3 spots to the left. So my decimal point there has to go 3 spots. I go 1, then after the 0 to go 2 and 3. So 0.0032 kilograms. From centimeters squared to meters squared. If I look at my chart, I have meters, decimeters, centimeters. To get from centimeters to meters is 2 spots to the left. But again, these are squared. Because they're squared, every spot on the chart is 2 decimal places. So this is going to be 4 decimal places that we have to move in our number. So the decimal point's right there. We go 1, and then we have to add zeros to go 2, 3, and 4. So this is 0.0001 meters squared. And now as we divide this out, 0.0032 divided by 0.0001 gives us 32 kilograms over 1 meter squared, or 32 kilograms per meter squared. So the conversions with metric units are great. We just have to move the decimal points. The problem with our rate conversions with metric units is not all of our units could be converted to metric. One of those is time. Any time that we have time involved in our units, we still have to come back and do some sort of a conversion factor. For example, if I tell you that we're going 25 meters per second down the highway, we want to convert that into kilometers per hour. Well, my 25 meters per second will become 25 meters over 1 second. And I can go ahead and convert my 25 meters into kilometers. From meters to kilometers, it was 3 spots to the left on our chart. So our decimal point has to go 3 spots to the left. Well, there's no decimal point here, so it starts at the end of the number. We go 1, 2. We have to add a decimal to go, or 0 to go 3. That is 0.025 kilometers. Over, we haven't done anything with our 1 second yet. To convert our second to hours, we have to go through our normal conversion method here. I'm using a conversion factor. Now, seconds are on bottom, so I'm going to put seconds on top. Now, I am going to cheat and do this all in one step. A lot of times we go from seconds to minutes, minutes to hours. Well, I know it's 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600 seconds in 1 hour. So the seconds cancel out. On top, we have 0.025 times 360, or 3,600, which is 90 kilometers, over 1 times 1 hour is 1 hour. So that nothing to divide out there. That is simply 90 kilometers per hour. 90 kilometers per hour is about 56.6 miles per hour. So as we can see, when we throw in time, we actually have to do a combination of conversions, doing the metric conversion and then doing the standard unit conversion for the time portion of our rate. With that, brings us to our last conversion for this unit. And that is the one that doesn't work out nice and clean, the one that we cannot simply use a unity fraction or a conversion factor for. And that is temperature. The problem with temperature is that there's no natural 0 point. At least there wasn't at the time when they developed the scales for measuring temperature. Now modern chemistry has discovered something called absolute zero, which is negative 273.2 or negative 456.3. Depending on which scale you're using, it's negative 456.3 degrees Fahrenheit, negative 273 degrees Celsius. Absolute zero means there's absolutely no heat. That is the only logical 0 point. Problem is, in nature, nothing is really that cold. We have to work really hard to get things even close to that temperature to do anything with them. So in everyday practice, that 0 point is far enough out that we don't really acknowledge it. Because of that lack of a natural 0 point, we have to do something different when we convert temperatures. Now, to clarify what I mean by a 0 point, like for length, 0 centimeters is equal to 0 feet, which is equal to 0 inches, which is equal to 0 meters, which is equal to 0 yards. Doesn't matter what unit I'm using to measure it, it's 0. Or 0 gallons is equal to 0 liters, which is equal to 0 quarts, which is equal to 0 pints, which is equal to 0 milliliters. Doesn't matter, again, what unit I use to measure it. 0 is 0. Unfortunately, we don't have that with our temperature. Our standard measurement for temperature is degrees Fahrenheit. Our metricized or metric version of temperature is degrees Celsius. Both of them use the same thing for common benchmarks, and that is water. It is the temperature at which water freezes. Or if we go in the other direction, the temperature at which water thaws, and the temperature at which water boils. In degrees Fahrenheit, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. In degrees Celsius, water freezes at 0 degrees and boils at 100 degrees. Because of this, there's 100 degrees between water freezing and water boiling. The Celsius temperature scale has sometimes been called the centigrade temperature scale, centi meaning 100, grade meaning division, so 100 division. Makes sense. That name has kind of faded a little bit in recent years. But that's what they're talking about, is that 100 divisions or 100 degrees between freezing and thawing of water. So two things that stick out here that we should acknowledge. The first is what I mentioned before. No natural zero point. There isn't a temperature that is 0 degrees in both scales. That causes a problem. Second is, from water freezing to water boiling in the Fahrenheit scale, it's 180 degrees Fahrenheit difference. In the Celsius scale, it's 100 degrees Celsius difference. What this gives us is a ratio that 180 degrees Fahrenheit over 100 degrees Celsius is equal. That's a conversion factor. I can reduce that down. I'll cancel out the degrees and get rid of the Fahrenheit and Celsius. I'll just work with the numbers. Both 180 and 100 can divide by 20 to give us 9 to 5. That 9 to 5 ratio or equivalency is one of the keys in converting between these. For every 9 degrees Fahrenheit, I'm going to put the delta in front of it. That means every change of 9 degrees Fahrenheit is equivalent to a change in 5 degrees Celsius. The temperature themselves isn't equal. 9 degrees Fahrenheit does not equal 5 degrees Celsius, but a difference of 9 degrees Fahrenheit is equivalent to a difference of 5 degrees Celsius. And then, of course, the other big difference, as I said, is this difference of 32 degrees between their 0 points. So to convert, I can't just use a conversion factor. I have to use a formula. If I have the temperature in degrees Fahrenheit and I want to go to degrees Celsius, my Celsius temperature is going to equal my Fahrenheit temperature. I subtract 32, that makes up for that difference in 0 points, and then I multiply by 5/9. So let's take human body temperature, 98.6 degrees Fahrenheit, and let's see what it equals in degrees Celsius. So what I'm going to do is I'm going to come over here and I'm going to replace the F with my Fahrenheit temperature. 5/9 times 98.6 minus 32. I do the subtraction here inside the parentheses. 98.6 minus 32 is 66.6. The parentheses have been combined to a single number, so I don't need them anymore. But I do have to put in that multiplication up front. 5/9 times 66.6. Now, if you're going to do this on your calculator, you don't have to actually use the fraction 5/9. You can just do 5 divided by 9 times 66.6, which will give us 37 degrees. That's 37 degrees Celsius is that temperature. If I want to convert from degrees Celsius into degrees Fahrenheit, my formula there is I take my Celsius temperature I'm going to multiply by not 5/9, but 9/5, because I'm going the other direction. It'll be the reciprocal of that conversion factor. Then I have to add that 32-degree difference for the difference in 0 points. So let's say we hear on the radio that it's going to be 20 degrees Celsius today. Is that a day to look forward to? Well, let's replace our 20 here, or our C here, with 20 and see what that works out to be. 9/5 times 20. Well, again, 9 divided by 5 times 20 actually turns out to be 36 plus 32. And finally, we add 36 plus 32 is 68 degrees. So yes, that would be 68 degrees Fahrenheit. I would very much welcome that temperature any day now. Okay, so that does finish up our Unit 2 here. Remember, Unit 2 test will be in class on Monday. The last day of February, we'll finish up our last day of Unit 2. Practicing what we talked about today. Page 118 out of the book, 1 through 19, the odds. And page 123 out of the book, problems 1 through 21, the odds. Deal with temperatures and some of these apothecary unit conversions. You may want to step back, page 114, 1 through 25. We assigned that on Wednesday, but that is our dimensional analysis, the rate conversions. So that might be something to go back and take a look at if you didn't finish that as well. With that, you guys have a great weekend. Hopefully we'll see you all on Monday.